couple of videos, we were dealing with first order differential equations with constant coefficient and constant term. We also applied it to the dynamics of market model. Okay, but look, first order differential equation with constant coefficient and constant term is the case of the simplest possible differential equations. So, of course, its ability to model different economic phenomena is rather limited. So, what I wanted to do with you now is an extension of it to the case of first order differential equations with variable coefficient and variable term. So look, how would equation like that look like? We would have dy dt. Of course, we need to have derivative in differential equation, then plus u as a function of t times y, which is also a function of t, and equals to w as a function of t. So look, what do we have over here now? Look, we have, instead of a, we have some function of time, but look, this is a function of time alone. It does not include y. And the same is over here. So here we have some function of time, and now, previous methods of solution will not work, of course, because we have a lot of changes, but as it turns out, obtaining at least part of it will be quite easy when it comes to complementary function. And look, we're gonna find a solution to this differential equation, and we're gonna do it very similar like we did previously. So first, what we're gonna do is we're gonna start with the homogeneous case. Okay, and look, if we got homogeneous case, here we simply have 0. So now our equation became simpler, and we need to solve just this. Okay, and probably you already know how we should approach this problem. First, we should take this to the other hand side of the equation. And, of course, now the good thing to do is to move y to the other hand side. So we have 1 over y times dy dt equals to negative u of t. Okay, and look, the trick to it is the same as we had previously. What should we do? Just directly integrate both sides with respect to time. So, we get dy dt over y dt, and it equals to integral of negative ut dt. Okay, so what can we do with this? Look, here of course we can use logarithmic rule. Look, I'm not going to do this in two ways like before. Let's assume that this variable is an economic variable, like GDP, price level, or level of production. So it cannot be negative. So in this case, we will get that here I have ln y plus some c, and unfortunately over here there is not much we can do. Look, we don't know how this function looks, so the only thing I can do to make it look a little bit nicer would be to take minus out of the integral. Okay. Now, just as before, I'm going to move c to the other hand side of the equation. Okay, let's make it into c1, and here we will have ln y equals to negative integral u t dt, and let's make it into plus some c. Okay, we can juggle with c quite a lot because it's arbitrary, so we don't need to put that much effort to it. Okay, what would be the next step? Well, the next step would be to take anti-log. And if I'm going to take anti-log, I'm going to end up with e to the power ln y equals, and because here we have plus, I'm already going to separate those two expressions. E to the power of c times e to the power negative integral u t dt. Okay, look, maybe from this moment on, just to make things simpler, I'm going to get rid of t out of u. We need to remember that u is still a function of time, but writing this over and over, we just make things more complex, so we just keep it like that, right? Okay, and now we remember that this expression is simply equal to y as a function of t. Then this is some arbitrary constant a, and here we've got just e to the power negative integral u t, where a, is an arbitrary constant equal to e to the power of c. Okay, so what have we established through this process? We have found complementary function. Right? And look, this complementary function actually is even very, very similar to the one we had before. We have some arbitrary constant. Here we will have deviation from equilibrium, right? And here we will have e to the power of some expression that will tell us whether we have a convergence or divergence. Before it was negative at, because integral, if this would be a constant, this solution would still be valid. We would have here negative at. So, like we had with in the equation, with constant coefficient and constant term. Okay, so now let's make an example. Let's just say that we have a differential equation given by dy dt plus 3t squared y equals to 0. Well, we clearly see that this is a homogeneous differential equation. We've just found the method of solution, so why not apply it? And look, what is our u in this case? Well, u is simply 3t squared. Okay, so now all we can do is to use the formula. So we've got y of t is equal to a times e to the power negative integral u dt, and all we gotta do now is to start substituting, right? So we've got that this is a to the power a times e to the power negative u 3t squared dt. Okay, and look, if I'm going to integrate 3t squared, what am I going to get? Look, that would be integral of t squared is t cubed over 3. So 3's are canceling each other out. And what I'm getting here is a to the power e minus have here C. But look, again, this is an arbitrary constant, and this is an arbitrary constant. So I can rewrite this as A to the power of E minus T to the power of 3 times E to the power of C. So look, those two are arbitrary constants. I can just write it as A times E to the power negative T cubed. Okay, and look, from this moment on, every time when we have a situation in which we will have an arbitrary constant in the power of E, and in general, we will be merging it with other arbitrary constants. Look, because it's no point to do this, as at the end we will only end up with this. And look, the rule here is simple. Like, as long as there is an arbitrary constant, when we perform integration, we see that it can be merged, we just can skip it, because it could go into A. Okay, so now that we've dealt with this, we should go to the non-homogeneous case. So, we go back to the original differential equation, dy dt plus u times y equals w. When we remember that u is a function of time and w is a function of time. And look, before, the only thing missing for us now is particular integral, so equilibrium solution. Before we were doing it by taking trial solutions, right? We're trying different solutions, which one works, this one we're going to use. Now, that was possible because we had constant term. With constant term, there's only limited possibilities that we can exploit. In here, when w can be any function of time, this is no longer possible. Of course, we could be lucky and find the right solution the first time, but again, this is not how we should do it. We should make a formal proof. Okay, and look, this formal proof is going to be a little bit lengthy, and it's going to involve two things you don't know. First, this is the knowledge about exact differential equation, and the second about integrating factor. Okay, so look, now what I'm going to do is I'm going to introduce exact differential equations, and I'm going to introduce, and later in the next video, I'm going to introduce integrating factor. This is not, but don't worry, math is not going to get very complicated. It's just a couple of tricks we need to use. But what I don't want you to worry, it's not going to be on the exam. I just want to show you exactly where the result is coming from. Okay, so let me just erase the blackboard. And let's move on to the subject of exact differential equations. Okay, so let's just say that we have some function of two variables, of variable y and variable t. Just like in our differential equations, we have two variables, y and t. Then, this is equal to some constant c. Now look, I can easily calculate differential for this for this function. So d f y dt is equal to, and look, here we have two sources of change. Y, so f can change as a result of changing y, and f can change as a result of change in t. So we need to have just two partial derivatives, df dy times changing y plus df dt dy. Now, what is the differential of a constant? Well, constant is not changing, so it's different. So differential of this constant must be equal to 0. And look, this is the part that we are interested in. And look, what you see over here is the exact differential. This is exact differential equation. And look, we're going to be writing it in the following form: as m dy plus n. Oh, of course, here should be dt. Here, I said dt, written dy. I'm sorry. Actually, it's very early, and you know that I'm really bad in the morning. Okay, so we've got n dt equals to 0. Okay, so look, the equation you see in front of you, this is a differential equation. This is exact differential equation. And look, what can we say about it? Well, we know that m is equal to partial derivative of f with respect to y, and we know that n is equal to partial derivative of f with respect to t. Okay, but look, now we can get a differential equation in this form. Look, we clearly see that, I know that this form is not familiar to you as much because this far we were doing this like that. But look, if I'm going to divide by dt, both sides, and then I'm going to divide by m, what would I get? I would get something that you're more familiar with. That would look like dy dt plus n over m, right, equal to 0. So, look, of course, this expression is a function of y and t. So, what we get is the homogeneous differential equation that we were dealing with before. But look, of course, this is not enough. Look, in this case, m and n can be any numbers, right? It can be any functions, any numbers. So, for us to be sure that this is a differential equation, we need to be sure that m is equal to df dy and that n is equal to df dt. So we need to devise a formal test that would allow us to do it. And actually, as it turns out, you know this test very well from mathematics class and from introduction to economics class. I hope that you remember something called Jung's theorem. Jung's theorem is simply saying that if I'm going to have a derivative, a second derivative, of, if I'm having a derivative of some function, and another derivative of partial first derivative of some function, then look, if I'm going to now take this function, and I'm going to differentiate it for the second time, but now with respect to t, if I'm going to take this derivative and I'm going to differentiate it for a second time, but now with respect to y, what should be the relationship between them? Well, I hope you remember those should be equal. Remember, we were always saying that Hessian is symmetrical, right? This is why we just needed to calculate part of the Hessian and not the whole thing, because of the Jung theorem and the symmetry between second partial derivatives. Okay, and this is actually bringing us to a point. Because look, it means that given any equation, given in this form, right, can have different things over here. But it's going to be exact if and only if the second derivatives are equal to one another. Okay, we're going to call it a test of exactness. Okay, a test of exactness. Okay, and how does this work? Look, we need to just take our m that we have over here and differentiate m with respect to time. And this outcome should be equal to the expression that we're going to get if I'm going to take n and I'm going to differentiate it with respect to y. So look, if this equation holds for a given differential equation, we can say that this equation is an exact differential equation. And this is the type of equation, of course, with which we want to deal with. Okay, so now let me just illustrate this with a simple example. So let's just say that now we have equation 2 yt dy plus y squared dt equals to 0. Okay, and now look, our job is going to be to test if this is an exact differential equation. Okay, and let's just do it very slowly. So here we see that this is our m and this is our n. So we've got that m is equal to 2yt, while n is equal to y squared. Now, what should I do with m? I should differentiate it with respect to t. So let's do it. I'm getting that this is 2y. Now, what should I do with n? I should differentiate it with respect to y, right? What am I getting? 2y. So now look, we know for sure that this differential equation is an exact differential equation. So we can work with it. And look, once we've established that a given differential equation is in fact exact differential equation, what we can do is to apply a very standard 4-step method of solution. Okay, and this is what we're going to do now for the example that we've got over here. Okay, so method of solution. Okay, so again, we've got the same differential equation. It was y squared dt. Okay, let's do all the preliminaries as we did before. So we know that m, of course, is equal to 2yt, n is equal to y squared. And what we also know is that this equation is exact because dn dt is equal to dn dy, which is equal to 2y. And look, at this moment, once we've established this result, we can go to this four-step procedure. Okay, and look, what we're gonna do now is that we're gonna integrate m. So, okay, step number one. Okay, so what we're gonna do here is that we wanna find f, y, t, right? Because we just know what are the derivatives of this, but we don't know how to get them. And look, so what is the first thing we're gonna do? Look, we're gonna integrate m. Okay. And because m is a derivative of f with respect to y, we need to integrate it with respect to y. But then you might say, what about the other part, right? We are just dealing with this, right? We have integral of m dy, which is just the first part of a differential equation. What about n dt? And of course, we cannot forget about it. So we are introducing a supplementary function. Let's call it psi of t. And look, we will hear psi is in this case associated with differentiation with respect to time. So this should suffice. And what we're gonna do here, we just simply gonna get what we get. So the part associated with m, and then we're gonna figure out how to get the part associated with n dt. Okay, so let's go to integration. Okay, so I just substitute for m. This is 2yt dy. Okay, so of course plus c of t. Now, here integration is very simple. We're treating t, of course, as constant. Y turns into y squared over 2. So what we get is y squared t plus c, right? But again, just as before, and we're gonna make actually a habit of it, we don't need to have c over here. Why? Because if this is some arbitrary function, why not put this c into it? And this is exactly what we're gonna do. We are gonna assume that this function already contains an arbitrary constant. Okay, so now we can proceed with step number 2. And step number 2 is differentiation of the result from 1 with respect to t now. Okay. So if we'll go through this step, what are we getting? Okay, so look, in this case, we're gonna obtain derivative of this with respect to time, right? F of t. Have we seen this derivative derivative somewhere? Well, this is our n. So now we see we are actually getting somewhere. Okay, so what we need to do now is to differentiate the entire expression that we had over there. Y squared t plus psi of t. You know, I'm going to use brackets here. And look, of course, we can differentiate these two expressions separately. So look, out of this part, I'm just going to get that this is y squared. And over here, again, I don't know what is the form of this function, right? So all I can write at this moment is that this is the first derivative of this function. And that's it. This is the function of time alone. So all I need to do is to add prime. But remember, of course, that this prime is over here, and it is here for a reason. Okay, so we arrived here at a very interesting step. Because look, what do we get out of this? We know that df dt is equal to n, right? And we know that n is equal to y squared, right? So, if we're going to take these both results together, we know on one hand that n is equal to y squared plus psi prime t, and n is equal to y squared, then consequently psi prime must be equal to 0. Right? Okay, and we are very, very close to solution because we are already at number 3. Okay, and point 3, step 3 is integration of psi prime with respect to t, right? There wouldn't be a point in integrating with respect to y, as we already did in the point number 1, right? So, what we're going to do in this step is that we're going to take psi of t and we're going to integrate it. Okay? So, but as it turns out that in our example, psi prime of t is equal to 0, we are just integrating 0 with respect to time. Okay. What we're going to get now out of this? Well, we're going to just get some arbitrary constant k. Okay, so now we need to, we can go to step number 4, and step number 4 is to combine, is we need to get a combination of what we got in step number 1 and in step number 3. Okay, so look, again I can write simply fy of t, and we get that this is equal to, or we got there that this is y squared t. Now, instead of psi that we had over there, I can just write k, right? Because look, by integration of psi prime, I just got psi. So I can substitute for psi, and I'm going to get that this is some k. Okay, and we are very close. We are very close to the solution if we notice one simple thing. We also said at the very beginning that this is the form of the function we were dealing with. F y equals f as a function of y and t equals to c. So look, we just need to compare these two sides, but again, because we get result yt plus k equals to c, it's not a problem. If I'm going to merge k into c, because it is an arbitrary constant, again, we can do it without any problem. So look, I am getting here y squared t plus y squared t, equals to c. And now, the only thing I want to do is to solve this equation with respect to time. Okay, so look, first thing I would do with respect to, y. So first thing I'm going to do is to divide both sides by t. And if I'm going to divide both sides by t, I'm going to get that y squared is equal to c times t to the power negative 1. Right? Now, what is the next thing I need to do here? Well, I need to take both sides to the power of 1 over 2. And as a result, I'm getting y of t equals to c to the power 1 over 2 times t to the power negative 1 over 2. And look, again, because c is an arbitrary constant, we get that we can actually write here y of t is c times t to the power negative 1 over 2. And this is how we solve exact differential equation. Okay, let's just do one more example and we can stop. Okay, so now let's say that our equation is given as t plus 2y times dy plus y plus 3t squared dt equals to 0. Okay, as before, we start with preliminaries, which are, first, what is our m? Well, our m is equal to t plus 2y. And what is our n? n is y plus 3t squared. What is the first thing we need to do? Test if this equation is actually an exact differential equation. Right? So, first thing I'm going to do is to differentiate m with respect to time. And I'm getting that this is 1. Okay. Then I'm going to differentiate n with respect to y. Well, it's 1 again. So we know that this is an exact differential equation. Okay, so now we need to go to 4-step procedure. We go to step number 1, and we're going to integrate m with respect to time. Okay, so if I'm going to, so here we're going to have f y of t, and it's equal to integral of m, not with respect to time, of course, with respect to y. plus some psi of t. Okay, so let's start integration. And so we've got integral of t plus 2y dy plus ct. Okay, so look, out of this I'm going to get ty, and out of this I'm going to get y squared. Again, arbitrary constant is going into c. Okay, so we've dealt with the step number 1, and as we dealt with step number 1, we can move to step number 2. So what we're going to do now is that we're going to differentiate this result with respect to time. Okay, so we differentiate f with respect to time, and what are we getting here? Look, out of this I'm getting y, then I'm getting 0 plus psi prime. Okay, but now, remember, we also know that n which is df dt is equal to y plus 3t squared. What are we getting from this? That psi prime must be equal to 3t squared. Okay, so, maybe I'm going to use this not to waste time. Okay, and in the next part, we're going to perform integration of psi prime with respect to time. Okay, and we know that this is 3 integral of 3t squared dt, which will give us which will give us, of course, t cubed over 3 times 3 t cubed plus some k. Look, we are not using c over here because this k needs to merge in with c a little bit later, so we just don't need it. Okay. And again, we need to combine the result obtained in point 1 with the result obtained in point 3, right? So first we get that this is ty plus y squared and plus, correct? Yeah. Plus t to the power of 3 plus k. Okay, so finally we are getting to the last step, and this last step is that we need to compare the two. And again, we can merge k with c, and then we are getting the differential equation with ty plus y squared plus t to the power of 3 equals to c. Okay, well, look, we would like to express it, of course, as a function of y, but till this end, we would have to, look, we can do it. This is not a problematic thing, because look, we can treat it as a quadratic function, right? Merge c with, put c on the other hand side, treat y squared as x squared, ty as bx, and t to the power of 3 minus c as c. You know, from the quadratic equation, we would need, and then we would just have to solve. But look, this would be time consuming. It would not bring us a lot of either joy or additional information. So let's just leave it as that. This differential equation that you see, this equation that you see over here can be solved to get the time path of y. Okay, so thank you very much for your attention. In the next video, we're going to deal with an integrating factor.